Good afternoon, students. Welcome to the next session on Module 4, that is Chemical Oxygen Demand. Now, what is Chemical Oxygen Demand or COD? It is defined as the amount of oxygen in milligrams that is required to oxidize the organic and inorganic impurities present in 1 liter of wastewater using strong oxidizing agents such as potassium dichromate, that is K2Cr2O7. And higher the amount of COD, it indicates more amount of oxidizable impurities in the sample of wastewater. Now, determination of COD of wastewater samples. Now, what is the principle that is involved in the determination of COD? See, it involves the addition of excess of standard potassium dichromate solution and sulfuric acid to the wastewater sample. Okay. Thus, potassium dichromate along with sulfuric acid is used because potassium dichromate, it is a good oxidizing agent only in presence of an acid. Okay, so potassium dichromate, it will oxidize the impurities present in wastewater. The amount of unreacted potassium dichromate, it is determined by back titration with standard solution of ferrous ammonium sulfate. And the amount of dichromate initially added to the wastewater is determined by blank titration. That is, instead of wastewater, we'll take the same amount of distilled water and titrate it against standard solution of ferrous ammonium sulfate. Now, the difference between blank titration and back titration values, it will correspond to the amount of FAS, that is equivalent to the amount of potassium dichromate actually used up for oxidizing the impurities. Okay, now let us see the procedure for determination of COD. Now first is back titration. Here, now what are the impurities that are present in wastewater? The impurities present in wastewater are straight chain hydrocarbons, aromatic hydrocarbons, pyridine, etc. Okay, so a known volume of wastewater, it is taken in a 250 ml conical flask. To that, we are adding 1 gram of mercuric sulfate and 1 gram of silver sulfate. Here, silver sulfate, it acts as a catalyst for the oxidation of straight chain hydrocarbons. Whereas, mercuric sulfate, it will prevent the interference of chloride ions present in wastewater, because when we are using silver sulfate, there are chances that silver, it will combine with the chloride ions present in wastewater and form silver chloride precipitate. So to avoid this, we are using mercuric sulfate. So mercuric sulfate, it will combine with the chloride ions and get converted to mercuric chloride, and thereby the interference of chloride ions, it will be prevented by making use of mercuric sulfate. So known volume of the wastewater along with 1 gram mercuric sulfate and 1 gram silver sulfate, it is taken in a 250 ml conical flask, and to that known amount of potassium dichromate and sulfuric acid is added. Now this mixture is refluxed for 2 hours. That means it is heated for 2 hours and then cooled to room temperature. Now the mixture is titrated against standard ferrous ammonium sulfate solution till the color changes from blue-green to reddish-brown using ferroin as indicator. Here first there is a blue-green color due to the formation of ferric ion indicator complex, and the color changes to reddish-brown at the end point due to the formation of ferrous ion indicator complex, and ferroin is used as a indicator. Okay, so this is back titration. Now in blank titration, the same procedure, it is repeated, but instead of wastewater, we will be taking distilled water. If we have taken 25 ml of wastewater, means here also we will be taking 25 ml of distilled water, and we'll do the same process. Now observations and calculations. Let the normality of FAS solution, let it be NFAS. Okay. Volume of FAS consumed for back titration, let it be Y centimeter cube. Volume of FAS consumed for blank titration, let it be X centimeter cube. And 1 centimeter cube of one normal FAS solution, it is equivalent to 8 milligram of oxygen. So 1 centimeter cube of N normal FAS solution, it will be 8 into normality of FAS, that much milligram of oxygen. So here X minus Y centimeter cube, it will give the amount of potassium dichromate that is equivalent for oxidizing the impurities, that has been used up for oxidation of impurities. So X minus Y centimeter cube of N normal FAS solution, it is equal to 8 into normality of FAS into X minus Y, that much milligram of oxygen. Now we have taken here V centimeter cube of wastewater sample. So V centimeter cube of wastewater sample, it is equal to 8 into normality of FAS into X minus Y milligram of oxygen. So for 1 centimeter cube or 1 ml of wastewater sample, it will be this divided by volume of wastewater sample that is taken, so much milligram of oxygen. So for 1000 ml of wastewater sample, it will be 8 into normality of FAS into X minus Y into 1000 divided by volume of wastewater sample, that much milligram of oxygen. So COD of the wastewater sample, it will be 8 into normality of FAS into X minus Y into 1000 divided by volume of wastewater sample, that much milligram of oxygen per liter. So volume of the water sample taken, it can be 20, 25 or 30 ml. Okay, so this is the calculation that is involved in determination of COD of the wastewater sample. It is expressed in milligrams of oxygen per liter. So this is the equation that you have to use for determining the COD of wastewater sample. Now let us do one numerical. That is 25 cc of wastewater. It was mixed with 25 cc of potassium dichromate, acidified and refluxed. The unreacted potassium dichromate required 8.2 cc of 0.2 normal FAS. In the blank titration, 25 cc of potassium dichromate acidified required 15.4 cc of same normal FAS. Calculate COD of the wastewater sample. So here what are the data given? X is given, that is X means the value that is obtained during blank titration, that is X, that is 15.4 cc. Now Y, that is for back titration value, that is unreacted potassium dichromate when it is titrated against FAS, that is back titration, that value is 8.2 cc. So X value is given, Y value is given. Volume of wastewater sample taken, it is 25 cc. And normality of FAS, it is given 0.2 normal. So solution will be COD value is equal to 8 into normality of FAS into X minus Y into 1000 divided by volume of wastewater sample. So much milligram of oxygen per liter. That is 8 into 0.2 into, substitute the values for X and Y, 15.4 minus 8.2 into 1000 divided by volume of wastewater sample taken, it is 25 cc. So you will get the answer as 460.8 milligram of oxygen per liter. So that's all for today's class. Thank you.